Well, thank you so much for that fantastic introduction. So this seminar is going to be different from some of the other ones I've given. There is nothing large about the stuff I'm going to be talking about. The examples, let me see if I can get these back up here in a second, are going to be, I believe, 2x2 matrices. So we'll look at some 2x2 matrices here. On the final slide, there will be something a little bit larger. I think it's a 50x50 matrix. I had a bit of a spiel prepared about this talk, and I didn't know what Michael was going to say. But this is, I would say, some of the most beautiful mathematical work I've ever done. So what you guys will see here is just remarkably pretty mathematically. So this, I guess at this point I'll just jump into it after mentioning that this is work with my postdoctoral advisor, Hen Greif, and actually his advisor, Jim Vera, up at UBC. So Vera and Saunders will be back here for a celebration called SVG 70 on January, is it 25th? Is that right? All right. So if you're here now, you should definitely be back here on January 25th for SVG 70, for what is sure to be an excellent one-day collection of talks. There's a website out there if you just Google SVG 70. All right, so what the heck are we going to talk about, and what the heck are circulant algebras and matrices and power and Arnoldi methods? All right, back so I guess I should set the stage for this work a little bit. There's been a lot of interest in ways of working with three-way data. So taking what we know about linear algebra and moving it up a dimension. So we know how to do all of this work with two-dimensional matrices and vectors. A lot of data sets out there aren't necessarily well described by two dimensions, and a lot of problems aren't necessarily described by two dimensions either. So there's been a long line of work that takes these things and looks at cubes of data or cubes of numbers instead. So one of the more recent contributions here was by Kilmer, Martin, and Perron in 2008. And they presented what we're going to call in this talk a circulant algebra. So this is a way to take a lot of what we know about matrix algebra and generalize it to working in a particular type or with three-way data, so a triplet of data or a data cube in a particular type or in a particular way. So in a nutshell, what they're going to do is the way they're going to generalize matrix algebra is take a cube of data and treat it as a two-dimensional array of one-dimensional things. Okay, so think like these data cubes are going to interact like matrices and vectors, except the vectors are going to be these thick entities now. So we'll go through all of their definitions. But when we started this work back in 2008, they had basically gotten through doing your basic your basic linear algebra operations, and then they had just started to get to spectral decompositions of these things. So what we've done and what we'll see in this talk is to take this algebra and basically, I would say, plug all the little holes you need to do almost everything you might be interested in doing from regular matrix algebra. So you can almost take an algorithm out of Jean Golub's book now and look at the operations, and there's almost a one-to-one map between those operations and what we have done in the new algebra. So you can do almost everything. So this is why I say it's mathematically beautiful, because everything generalizes in a very seamless way. So what we'll see here is what you need to get up to the power and Arnoldi method, and also some refinements of the existing theory. All right, this is the power method as you might implement it in a couple more than the one equation iteration. So what do we have here? We need a matrix and a vector. So this is a power method just on an n by n matrix. So you've got your n by n square matrix, you've got your initial vector x naught, and you've got your stopping tolerance tau. So what do? You normalize your vector. So I'm going to write the normalization in a funny way. We're going to multiply by the norm of the vector inverse. All right, so it's just scaling that vector. And then you iterate until convergence. You multiply your matrix by a vector. You take a norm. You rescale that vector by the norm, and then you check how much that vector's changed. So there's a bunch of different stopping criteria. This one has the nice property that you look at when your vector actually converges. Now your vector might be flipping signs, so you need to make sure that the sign of your vector is the same from iteration to iteration. This is fine because eigenvectors are unique up to a sign. All right, so what are the operations we need to do this? Well, we need a scalar inverse, so that's this thing. We need a norm, that's this thing here. And we need this absolute value, which will end up coming out of the sign. So we'll see the relationship between sign and absolute value as they play out here in a second. You basically define sign by dividing a scalar by its absolute value. So what we're going to do is basically, take all of these operations and map them out into this new way of working with cubes of data. One thing I should also say is one of the reasons they want to work with these cubes of data is that there are particular data sets that Kilmer has worked on involving images, where this is a very natural way of sort of looking at some of the problems. So with that, let's look at what they're doing. So we're going to take a cube of data, m by n by k table of data, and we're going to look at this as a matrix, an m by n matrix, where every scalar has length k. So here's a nice little picture. We've got our cube of data. We're going to take things in this dimension and look at them as scalars. Some people call these tubes or fibers. I just think of it like this picture, and the stuff going into the board is the depth of your scalar. All right, how are we going to write these things down? For reasons that'll become clear in maybe a minute or two, I'm going to say that any type of three-way data in this talk is going to be a bold letter underlined. So some people like writing these with scripts. I can never write a script on the board, so I always underline these. As I said, we're going to treat these things mostly like matrices. So we're going to separate out the matrix dimension from the scalar dimension. So we're really looking at matrices over matrices of scalars that come from kk. So we're going to denote the space of these things by k sub k. Just as a quick preview, this will end up being a ring. So k is oftentimes used as a symbol for a ring. So the way they define this set of algebra, these scalars are going to interact like circulant matrices. Quick primer on circulant matrices. Just quick show of hands. How many people have seen these things before? Okay, so this is a quick review for most of you. So these are a commutative closed class under standard matrix operations. If you take circulant matrices, you multiply them, you get another circulant. If you add them, you get another circulant too. How are they defined? The structural definition is we have k numbers. We take those k numbers, string them all out along the first column of the matrix, and then we cycle them in the next column. So A1 moves from the 1, 1 position down to the 2, 2. Then we're going to get A2 down here. Then we're going to get all the way down to AK minus 1 here. And then AK cycles around the top. So by the time we're done at the nth, or at the, I guess, kth in this case, kth column, we've got A1 in the last position, and then A2 through AK in the first rows. Some other people define these with your vectors going along the row. It's really a matter of choice. So here I'm doing your k numbers run along the first column. So these things have been studied for a very long time. I actually managed to dig up some of the references going back to Muir's long 4-volume treatise on theory of determinants. So he was, I believe, that was one of the first places these were sort of written about as we might describe them now. But these are not new things. We're going to just introduce a little bit of notation here to work with them. So I said that we're going to look at these matrices as tubes. So what we're going to do is take each tube of that and look at it as one of these elements, kk. So in order to make this a little bit more precise, if we've got, so this is looking at a scalar in our algebra now. So this is just one number in one of our matrices. So we've got alpha. Alpha is a scalar in this case. So Greeks are going to be scalars. Alpha under bar is going to be an element of kk, so a1 through ak. What we're going to define is a circulant matrix representation of this. So circ is just a different way of representing this scalar as a regular matrix object. So this just takes that, so this is sort of a subtle point. I'm not really saying anything at all here. What I'm just doing is setting up some notation to help us think about these operations. So you should think of these two as just two different ways of describing the same thing. So when I talk about it in the matrix algebra, it's easier to write this. When I do operations with it, it'll end up being easier to write this. So in particular, when I write alpha plus beta, what I'm going to do is just add the two circulant matrices together. Now, this is a particularly easy one because all that ends up doing is just adding the two vectors of scalars. But when we do multiplication, so circle will be the circulant multiplication in this case. We actually form the circulants and then multiply the circulants themselves. This is, one second, this preserves the fact that it's a circulant, and then we read out that first column if we want to get back to the individual numbers here. Yes?
You may have just said it, but so if you multiply two circulant matrices together, you get a circulant matrix?
Yes, yeah. So it's closed under this operation. So then we also define some 0 elements and 1 elements. So the 0 circulant is just the vector of all zeros. The identity circulant is just the vector 1, 0, 0, 0. So what happens if you write the circulant of this vector? You get i's along the diagonals and zeros everywhere else, which is exactly the matrix identity. So these are how these things interact. So at this point, we basically have all the operations we need to do linear algebra. So we've got identity element, we've got an addition operation, and a multiplication operation. Turns out we can extend this thing to these m by n by k arrays of numbers too. So bold A or bar here is going to be one of these tables, and if we want to multiply that by a vector, well, all we have to do is just sum up all of these individual terms here. So this is just writing out a matrix vector product where we've changed what addition and multiplication means. Turns out that this will have a really nice way of representing it in terms of these circulants. What we're doing in this operation is we're computing a circulant for each entry, and we're actually doing a big matrix vector product with a matrix that's got a circulant in the 1, 1 block now. So there's a big block there all the way out through the rest of the matrix. So if we want to do this operation in terms of our ring kk, it corresponds with this operation back in terms of standard matrices in linear algebra. So what we do then is we actually define circ of a matrix operation to just be the circ operation defined everywhere, in which case we can write these operations just in terms of circ of the sort of elements in of the elements themselves. So all we're doing here is just setting up notation and getting things set so we can get through our power method. So this is equivalent to what Kilmer, Martin, and Perron had done back in their paper. They did this all for a slight permutation of these matrices. So they did it a little bit differently than this, but it's equivalent up to a permutation of what they had done. So at this point, we can do matrix vector products with tables of numbers now. So we've got an m by n by k array of data. We interpret that as this m by n matrix of length k scalars, and then we multiply it against a vector. So what's a vector in this case? Well, this is a length k, a n by k dimensional data structure. So vectors look like matrices now. Yes?
You mentioned some things are commutative, so the bottom line, is that the same as alpha dot x?
Excuse me. Yes, I'm writing it this way because this is the way the matrix algebra actually works out. So if you think about the dimensions of what these things are, so circ of x is going to be, there's a board over here, right? Is there a marker? There is a marker. So circ of x underscore is going to be an nk by k matrix, and circ of alpha is going to be a k by k matrix. So that's why I've written it here with that at the end, just so that we can do the so the dimensions of the matrix work.
Not commutative, n is different from k.
Well, so they commute over here. The question is, does the operation, so all operations over here make sense if you just write them out in terms of sums and products. The question is, how does this representation work once you go over and look at it in the matrix as a set of regular matrices instead. Actually, I'll say that if you look at almost any block algorithm in regular linear algebra, what happens with scalar operations is that they almost always migrate over to the right-hand side of equations. So if you think about how to do the block power method, for instance, then when you do the scaling, what you're really doing is you're multiplying by the norm now on the right. So in some sense, we should always write scalars on the right, although that's not the point of this talk. All right, so where do we stand on what we have here? So we needed a scalar inverse. Why do I have scalar inverse checked here? No, okay, so we've got a scalar inverse. Remember I said that these things interact like matrices. So what's the inverse of a matrix? Well, we all know how to do that. So you just pretend Michael's not in the room and you write inv of A in Matlab. So our scalar inverse is going to just end up being a matrix inverse of a circulant. But we still have to do these norms and absolute value things. But otherwise, what we can do is we can take y is equal to, so here, what I'm doing is instead of doing this operation here in the regular power method, we're going to translate it into taking a vector and doing a circulant multiplication of the norm. We don't know how to do the norm yet, but if we did, then we just take that and invert that circulant. So you just do a circulant inverse here. Same thing here. You just write these things out as big matrices. So now let's see how we get norms and absolute values. So these are things that no one had proposed before we had come along and thought about them. All right, so in order to state these things, we're going to have to take another step back and look at circulants again. So it turns out that circulants are sort of tightly intertwined with Fourier transforms. So if C is a circulant matrix, then the eigenvector matrix of C is actually the Fourier transform matrix. So the discrete Fourier transform matrix F. This matrix has all sorts of beautiful properties, but practically what this means is that if we actually want to do all of these operations with circulant matrices, we don't have to do them in O of k squared operations. We can do them in O of k log k operations instead. So we take our vector of numbers, we hit them with a FFT in Matlab, we get a different vector of k numbers out of that, and then we can do matrix multiplies in O of k log k, which ends up happening just because the eigenvector matrices of all circulants are the same. So this is the last point. So, okay. Questions about circulants and Fourier transforms? That was a quick introduction, I admit. Okay, let's keep going. What we're going to do is we're going to define a little bit more notation. So this talk is very notation heavy, but the payoff is worth it, so I promise. If you have a circulant, one of these elements from our ring, we're going to define an operation called the CFT. So what does the CFT does? One of my co-authors didn't like calling this the FFT, which is what I wanted, or the DFT. So they wanted the circulant Fourier transform in this case. But all we're doing here is just, instead of representing this with a k by k circulant matrix, we're representing it with a k by k diagonal matrix, where the Fourier transformed coefficients are on the diagonals now. So let me write it on the board here, I guess. So before we had circ of alpha underscore is equal to alpha 1 all the way up through alpha k, alpha 2. So this wraps around. So this circulant Fourier transform of this is just a different representation where we take alpha, so alpha 1 or alpha I hat is equal to, I'll just write quote FFT of alpha. So it quotes there because that's not quite the right representation. But instead of representing this element of that algebra with a circulant matrix, we're now representing it with a Fourier transformed coefficient. So instead of representing a matrix, we're now representing the eigenvalues of the matrix instead. All the matrices have the same matrix of eigenvectors, so this is an equivalent way of talking about it. ICFT just takes this and inverts it. So if you think about it, ICFT is just going back to the original matrix. So you can write these both as basically Fourier transforms of this matrix itself. So the combination is an identity, and what will happen is if we use this representation, everything will make a heck of a lot more sense in our algebra. So in particular, we can now redefine addition and multiplication. So before we had circ of alpha plus circ of beta. Now we have the inverse CFT of CFTs. So here we just add the two again, and then we take the inverse CFT. Now, you wouldn't ever implement this way, but this is, again, just sort of talking about the notation. You would implement this one this way. So doing each of these steps is O of k log k operations, and then doing the matrix multiply with diagonal matrices is order k. It turns out that this entire notation generalizes to matrices too. So if you want to write A circ x, you do the inverse CFT. You define the CFT of A and the CFT of x, and you take the inverse CFT of that. Now, there's a couple little tricks in here, so let's get to those. I feel like they're there's a slide missing here. Hang on one second while I just make sure that there's nothing. I feel like there's a slide that should have been there, and I'm not sure why it's. Okay, it's coming up still. And for some reason, I was thinking I had it in there. Okay. Sorry about that. The picture. Anyway, I was mucking with the order of the slides, and I apologize. So when you want to do this operation in Fourier space, guys, we're going to skip ahead. This slide is absolutely sort of key to understanding what's going on. So I really apologize. I must have been thinking I could explain it a different way when I was sticking this together. So this figure sort of explains what's going on here when you take this operation and apply it to a matrix instead of an individual entry. So before we had seen this one, you take your matrix and you look at it with a circ. So this is just every block of this matrix becomes a circulant. So here, these sort of do repeat in the right order. If you take the Fourier transform of each of these blocks here, so that this would be taking each of those blocks and looking at the CFT of each of those blocks, then you're going to get a diagonal matrix here instead. So we can represent this with a Kronecker product times a Fourier matrix. So this is multiplying by this for all of these things replicated, and then on the right. What we're going to define as the CFT of a matrix is going to be a shuffling of this. So rather than have it be a matrix of diagonals, we're going to permute it into a block diagonal matrix. So this element here is going to become this element here. This element here is going to become this element here. This element here will become this element here. Likewise, this one here will become this one here. So there's a whole bunch of different names for this type of a permutation. Sometimes it's called a perfect shuffle permutation. That's Van Loan's preferred term. It's also called a stride permutation. It really corresponds to taking a vector of data. So imagine you have a matrix mapped out, laid out by columns in memory. So you've got the entries of your matrix laid out by columns, and you wanted to permute it to where the entries of your matrix are laid out in rows. So that's exactly the same permutation that does this transformation here. So all we're doing here is permuting it. One fact to note here is that there's going to be exactly k blocks of this matrix in the CFT. So the original matrix was m by n by k. This matrix here, every block is going to be m by n, and there'll be exactly k such blocks. So then when we want to do matrix vector products with this, what we're going to do is we're going to do all of those Fourier transforms, form that block matrix. You can do the same thing on the vector too. So each of these guys is going to be a length n vector. And then you're just going to do all those diagonal matrix products. So the work involved in doing this is, if you write it all out, this is how much work you have to do in the ICFT and the CFT, and this is how much work you have to do in all the matvecs. So this is a much better way of doing the matrix vector products than doing it in terms of Fourier matrices. All right, so I apologize. These slides have gotten totally out of order, so I'm not really sure what happened here. I'll have to check my logs of the edits. The reason we were doing all this FFT stuff is because we wanted to actually understand how to do these additional things, which were the norms and these scalar products. So what we're going to do to define all of these other operations is just apply them to the eigenvectors in the matrix. So this is exactly the same as doing functions of matrices. So I'm jumping all over the place here. I really apologize. I don't know. I thought I had these slides in the right order after I did a little bit of work on them. So let me. Okay, so the last thing that we were looking at was doing the matrix vector products with this FFT. What we're doing here is we're now going back and looking at operations on scalars. Once we do operations with scalars, using the CFT representation gives us a much better way of stating them. So the CFT representation is really looking at the eigenvalues of the matrix itself. So if you want to do a function of a matrix, you can apply that function to the eigenvalues of the matrix. So that's all we're doing for all these other definitions of functions. So if you want to take the absolute value of a circulant entry, compute its CFT, compute the absolute values of all the eigenvalues, and then hit it with the ICFT. If you want to do the conjugate of an element in the scalar, then you just take the conjugate of all of the elements of the ICFT. What's the conjugate of an element? Well, these are all complex valued elements because we're looking at the Fourier transform of a general vector. We also define something called the angle, so this will end up being the entry divided by its magnitude. So this is like the sine operation that we used in the power method. So now we have sines. Now you can do some cool things at this point. So it turns out that the conjugate of angle, the conjugate of angle, is always equal to the identity. Why does this make sense? Well, if you take the sine of any number, so if I have a scalar, if I take the sine of that scalar and multiply it by itself, I always get the number 1. So sine squared of any scalar is 1. This is the generalization of that fact to our new algebra. The proof of this ends up being about about 3 lines of just nice linear algebra. Now, I was going to do a Matlab demo of this, but I'm running a little bit behind on time because of this issue with the slides. So we're going to do a different Matlab demo in a second. Okay, so let me do a little thinking now that I know that these things are out of order and find the one I actually want next. So I apologize for this. Yeah, so for instance, this one is just I'm tempted just to do it on the board because it's particularly easy to do. So I. Okay. Well, so the next thing we need to work on is norm. So what I was doing here was just working through a simple example of what this stuff actually looks like. So for a very small example, this is just a worked out example of what these 3 different matrices look like. But I realize I'm confusing you guys badly here, and I really apologize. I should have taken a look at this much more closely before presenting it here, but I thought I had it right last night. So is it reasonably clear what to do as far as these operations? Okay, so we're going to skip through these things. So at the moment, we've gotten through everything except the norm. Let me tell you how to do a norm now. It's going to be the same type of operation. So the let me do it this way. So the norm of x is going to be x transpose x, and we take a square root of that. Except that's not quite the right norm. It's actually going to be x star x. So if you're familiar with working over the complex, we need to use the Hermitian there instead. So when we want to do the norm in our new algebra, we can just take all of these operations here and just write them out. So this is going to be circ of x, the conjugate transpose of that, times the matrix circ of x. This is going to be a scalar. So let's think about the dimensions of these things. This is going to be nk times k transpose times nk times k. So the outcome of this is going to be a k by k scalar. That's then going to be an element of our circulant matrix. So we can take the square root of that just as an element of our circulant, and we're done. So put another way, if we just write out, so another way of looking at this is we write out this norm sort of as a sum of products. This would be the sum of xi circ xi, except it'd be a conjugate in this case. Sum of I is equal to 1 to n, and we take the square root of that. All right, so this is a definition of the norm. One of these slides has some type of interpretation of that. It turns out we're also going to use the following inner product. So when we do a general inner product, we can show circ star of y is equal to just circ of y. This conjugate here is really important. None of this stuff works without it. Okay, so going back to the power method, we actually have everything we need now. So we've got norms, we've got scalar inverses, and we've got matrix vector products. So we can actually code and implement a power method now.
What are we going to get from it?
So what are we going to get from it? What should we get? So a matrix times a vector is going to give us another vector, y. What's our eigenvalue going to be? Matrix times a vector is equal to lambda, or I'm going to write it this way now, y circ lambda. So what we're going to get out of the power method running on this is going to be an eigenvector, which is going to, hopefully in some sense have some nice largest eigenvalue property. Yes?
In this context, is lambda like an actual scalar, or is it one of these?
Lambda is a scalar in kk, so it's one of our funny scalars. Yes?
How do you define the square root in kk?
So the square root in kk is just, so the square root of alpha circ is equal to circ of alpha to the 1/2. So this is the matrix square root operation. Or you can define it equivalently as ICFT of this is going to be the matrix where you take the square root of the Fourier transforms of all of your coefficients. Does that help? Yes?
So there's multiple square roots in this field.
So we use the, let's see, we only define this for positive ones. So you've got to be positive in order to apply the square root operation. Which then begs the question, in the norm, all are all of your eigenvalues positive? And they are, because what did you do? You did circ of x, which is a tall matrix, inner product, other way around. You did tall matrix transpose itself. So this always gives you a positive definite matrix. So all of those eigenvalues are always positive there. So the ones we need to take the square roots we're fine on. All right, so here's a quiz. If I run the power method on this matrix, what do you guys think will come out as a possible eigenvalue and eigenvector? Any guesses right here? Top left entry. All right, that's what I guessed too. Does anyone else have a different guess? Okay, turns out that's wrong. And let's just do it. So we have all of this stuff coded up in a Matlab package. So I'm going to clear my environment. I'm going to initialize a 2 by 2 by 3 circulant matrix. I'm just copying from the left over here so I know what to write. I'm going to set the 1, 1 entry to be CA scalar of 2, 3, 1. We have random number generators done. So we're going to get a 2 by 1 by 3. So what we're going to do is we're going to run the power method starting with a random vector 2, 2, 1, 3. So it runs and it spits us out things. So the eigenvector we get lambda is 3 and a third, 1 and a third, and 1 of a third. What was this matrix A we had? So this was 2, 3, 1, 0, 0, 0, 0, 0, 0, 3, 1, 1. So the eigenvalue we got is neither of these two entries, which is exactly what I expected it to be. It was to be one of those two entries, and that's not what it is. So this caused us to immediately think there was a bug in our algorithm. There's no bug in the algorithm. The situation is just more complicated here. Yes?
Okay, so lambda you got was, lambda up there.
Lambda up here, so it's a 3 by 1 scalar. So.
And then is that A up there? Is that your eigenvector?
What's the eigenvector? Good question. That's the eigenvector. So it's not the identity eigenvector in either of the two blocks. So the largest eigenvalue eigenvector in this case is some linear combination of those two entries of the matrix. What would that do? Oh, that's much nicer. Thank you. That's a handy trick.
What happens if your two elements, like in 1, 1, is 1, 0, 0, and then your 2, 2 is 2, 0, 0?
Okay, that'll work because we have a theory of what actually happens here. So took us a while to understand what goes on, but it turns out once you have a package to actually compute things, all of this insight goes much, much, much faster. So what is really happening? Well, it turns out it's really hard to understand unless you delve into this ICFT and CFT representation. So what we were doing before was taking this problem and looking at it in terms of this structure. that's not the right way to look at it. And this is what that ICFT tells us. It's also what linear algebra tells us in general. So if we take this matrix and look at its CFT, everything here is a element of K3. So we're going to get a block diagonal matrix now, where every block is 2 by 2. So these are the Fourier transform so the Fourier coefficients of this matrix, or so let's see. The Fourier coefficients of this vector here is here, here, and here. That's I, yes. I removed the dot on the top because it was confusing in one of the earlier drafts, which was using a weird font. Not real eigenvalues. They're not all real, no. So it turns out that if you pick the largest eigenvalue from each of these 3 blocks, you're going to get 6, 2, 2. The ICFT of 6, 2, 2 is exactly that 4 1/3, 1 1/3, and 1 1/3. So what we're really doing here is when we run the power method on this, we're taking this matrix here and we're running independent power methods on each of these blocks. So that's what's going on when we run this in the algebra. We're just doing replicated power methods on each of these blocks. The power method is going to converge exactly like we expect it to on those blocks individually. So they're doing standard power methods within these. So that's why when we run it, we get 6, 2, 2 out. These are the largest magnitude entries in this entire space. However, what this means is that there are a lot of eigenvalue, eigenvector pairs out there. So this entry, or 2 of the eigenvectors are exactly what you would expect. So the identity element in the 1 entry and the 0 element in the 2 1 entry. So that's also an eigenvector of this one. It's just not what you get out of the power method. So a standard matrix has n eigenvalues and n eigenvectors. These matrices end up having n to the k eigenvalues and eigenvectors. And that's my timer telling me I need to be done. Okay, so I apologize. This slide is really simple. What we actually are able to do is show that although there's n to the k eigenvalues and eigenvectors, there's only a special set of n that matter. So you define this special set by basically taking the largest one from each block, removing it, taking the second largest from each block, and repeating that. So the way you usually define an ordering of the eigenvalues of matrices is by the first eigenvalue is what comes out of the power method first. The second eigenvalue is what comes out of the power method second after you deflate for the first. This is exactly the same type of ordering here. Okay, so we also have a whole bunch of other small results in this vein. We can show convergence results for how quickly the power method converges once we have this analysis done. So effectively, once you look at this as repeating the power method on every block, all of the results make sense. So that's the way to state it, and I apologize for doing a poor job on this presentation. The same thing happens with the Arnoldi process. You do an Arnoldi process on each of these blocks in Fourier space. So you can use this to treat a partial differential equation. So how can you use this to treat a partial differential equation? Well, it turns out if you discretize this particular elliptic, or the Laplacian equation with a particular type of, why am I blocking on what it means for repeating boundary conditions? So if one of your boundary conditions wraps around, then you're going to get out a matrix that's exactly blocks of circulants. So what we're going to do is interpret this as a big n by n by k matrix in our algebra, except it's going to be little n by big N is your depth now. So it turns out for this special operation, it's one of these canonical operations. We can work out exactly what all of these canonical eigenvectors are. They have a particularly nice form. So the matrix we get out to look at this PDE ends up just being 4 cron I minus cron I all the way down. And then we can run both the power method here and the Arnoldi method here to solve this equation. The power method converges at the rate you would expect, which is the rate of the worst eigenvalue in all of your problems. So if you look at all the eigenvalue gaps in those K blocks, the worst ratio is going to determine the convergence over all of the iteration. That's exactly what we find here. So this is the convergence rates of all of the individual eigenvalues. This is what we would predict based on the worst one, and this is what we predict based on, this is what we'd predict based on the worst one, and this is what we'd predict based on the best one. This is the convergence of the eigenvector out here, and these are the eigenvalues, which converge a little bit more quickly. For the Arnoldi iteration, we don't get convergence before we would expect it. So in this case, you have to run the Arnoldi method for all n steps before it converges. And with that, I'm out of time. So all of this stuff is on Hen's page. It's actually on my page 2. We have code that I'm happy to send you, and it's linked off of my site as well. So I apologize for having the slides out of order, but thank you for being such a patient audience. This is the GVG paper.
It seems as though it might be possible to extend this definition of circulant to matrices of arbitrary dimension.
So when you say matrices of arbitrary dimension, you mean like 4 by 4 by 4 matrices, or
3 by 3 by 3 by 3, or 3 by 3 by 3 by 3 by 3.
Okay, yes. So there have been a couple of proposals by who was working on that one? It wasn't Misha. It was or was it? So there have been a couple papers since then that do talk about these extensions to higher order stuff. So I'd be happy to send you those references. But yes, you can generalize it further.
I wasn't sure if there was an easy way of saying just define the circulant to be the circulant of like I just noticed that one definition you had, like the circulant of vector thing was the circulant of its components.
Yeah. So basically, you can extend it, but one dimension has to stay special, which is this one that becomes the circulants.
Right.
So in your physical example, it made a lot of sense to choose sort of the way of looking at the matrix that you use in terms of this dimension is going to be the circulant, and the other two form the matrix.
The other two form, yeah.
I imagine there are applications that aren't physically motivated, where
So
you use different eigenvectors and eigenvalues.
there was a study of a closely related set of operations called the Fi R Matrix Algebra, and this was I want to say 1995. So this was studying a particular problem in signal engineering where they wanted to do, I don't want to misspeak and say that they were doing the wrong thing. So they wanted to do some type of signal analysis, and their problems there were with two by two matrices. They wanted to come up with 2 by 2 matrices that had very particular properties. So they came up with, I'd say, about a third of this type of analysis, motivated from a different perspective. But they focused on the 2 by 2 case, which if they had just written a couple more dimensions, they would have gotten most of this. But yes, there are applications elsewhere.
Sure. I guess going further, I guess my question was, if I have a block of data,
Mm-hmm.
data, if I look at it head on, I get these are my circulant elements.
Yes.
You know, the depth dimension, but I can also rotate it and look at it from a different slice.
So yes, you need to be careful with how you use this to analyze three-way data. So generally when people use this to analyze three-way data, they tend to use that third dimension to encode time, in which case you're doing a Fourier transform, or your circulants become your temporal dimension of your signal, which then sort of makes a lot of sense about why this would be useful. So Misha's done a lot of work with that on denoising images, actually, where they have some set of observations of an image over time. And so then a rank 1 approximation ends up giving you some type of picture out.
Do these relate in any way to like the canonical tensor factorizations that people come up with?
So that's an excellent question. The short answer is no. The longer answer is I'm sure they relate in some way, but that's an excellent open question. So this way of looking at data is sort of a little bit different from what people from that community look at. So for instance, when they define an eigenvalue, eigenvector of a tensor, they actually look at extrema of a linear form. So what we've done was try and generalize a lot of linear algebra. What they're doing is looking at sort of sets of polynomial equations. So they look at this thing they call t x cubed. So t here is a tensor. And what is this? This is really so you sum up over all ijk of the, I don't know, it's a multilinear form, I guess, is what we should call that. This is a 3 up here, in which case an eigenvector is just then a set of n numbers. So here an eigenvector is a set of n by k numbers. So it's a little bit different. But it would be cool if there was a nice crisp way of relating those two. We spent, I won't say a lot of time thinking about it, but we did try that for a little bit and didn't get anywhere. Yes?
I think I might be missing something slightly superficial, but okay, so not all the elements of the ring are going to have multiplicative inverse.
Yes, yes.
And then you're using the inverse of the norm. You know that, it's defined because the eigenvalues are going to be positive, but you don't, well.
No, you're right. So you caught one of the subtle problems with this. If any of your eigenvectors become 0, you sort of lose information about that dimension. That's what you're worried about, right?
Yeah, I mean, or the norm.
So you can sort of start fudging things with pseudo inverses. So pseudo inverses will more or less do the right thing, because if one of your eigenvectors became 0, that meant that effectively you had zeroed that dimension out of your norm, which meant that there was some redundancy in your system. So you want that to stay 0. So in some sense, for these operations, that's okay. But this is in general a problem. So we thought about how much of a problem that is, and then started looking at literature on block matrix equations. Everyone just assumes that doesn't happen. So we decided we were safe with that assumption for this particular problem. I've never run into it unless I unless I by hand construct an example.
David, how did you make those figures?
These are MATLAB.
Really?
Yeah, they show up better on the screen. So if I zoom in,
They look more fancy than normal MATLAB figures.
no, they're just normal MATLAB figures. So you can get MATLAB to do some strange rendering of tech if you ask it nicely.
But what about the gray lines?
You just tell MATLAB you want a gray line.
Yeah.
I think it's, what is it, plot. So the way I would do it is plot x, color, and then my preferred one is 0.55 times 1, 1, 1. So you should get a nice gray line if you do with that. Yeah, so let's see, what is the horizontal axis here? That should be iteration number, unless I've been mistaken. So there are a lot of iterations. So these, we're just, we're seeing a couple hundred or 50 or so dots in there. So you can see once they start to converge, this is 10 to the minus 15th here. They just sort of bounce around that level.
Okay, well, let me thank you very much, Dave.
Well, thank you guys. I apologize. I honestly don't know what happened with the slides. So thank you for being patient.